So, you've been here since the beginning of the week, so you know exactly that it is indeed possible to store data on DNA. And the way it is done, that we will create synthetic DNA molecules and made of nucleotides, and this will encode the information. And since you've been here since the beginning of the week, you know that it has many benefits. It's very compact, it lasts for a very long time, and it requires very low power upon storage. And you also know the workflow. You start from the data that you would like to compress. It can be a file, a binary sequence, an image. Then you encode it in order to get the DNA sequence. And then you will synthesize in order to get the DNA molecule. Then you can store it. It can be in a capsule that was shown to us yesterday. Then in order to retrieve the data, then you will sequence it, and then you will decode it in order to retrieve the original data. So everything you know. So now you may wonder, but why do I need compression, right? Since it is very compact. And we had already the answer. There is indeed a bottleneck. The bottleneck is a synthesis. It costs time, and it costs also computation and liquids, etc. So there is a need, indeed, to compress the data. And now also you may wonder, okay, but is the compression similar to the classical compression, or do I need a different compression if I want to do DNA-based data storage? So there is a yes and no answer. We can build upon classical compression, but there are specific challenges, and this is what we will see in this presentation. So I propose you 2 lectures. The first one is devoted to data compression. And I will mostly focus on the theoretical result, why we do data compression in that way.
I'll try to remove the bar.
Okay. Good, thank you. And I will also have a special focus on image and video. So the motivation for that is that 80% of the data that transmits over internet, it is image and video. So if you know how to compress image and video, you know how to compress almost a large part of the data that we exchange and that we create today. And in the second lecture, then we will go to data compression for DNA-based data storage. Okay, so classical compression for image and video is the following. So you have your data, your images, your video, you encode them, you get a file, and you can store it on a server. And if you want to retrieve your data, then you get the file, you decode it, and you can read it. Okay. But there is something that is very special to image and video, is that when you open the box of the encoder, you will always find the same steps. There is always a prediction, then a transform, then a uniform scalar quantization, and then finally entropy coding. So at the beginning of my career, I was not working in data compression. I was mostly working on channel coding. And that was the very first time I was very surprised. Why do you need all these steps? And this is what I would like to share with you today, is my understanding of this field. Why do we need these steps? And and mostly, what are the theoretical foundation of these many steps? And these steps, I will call them, or this strategy, I will call it divide and conquer. Okay? So in order to go through the process, I will start from the end, okay? We'll first look at why entropy coding, then we'll add a box, then another box, and then finally the 4 boxes. Okay, so let's start with entropy coding. So entropy coding is, in fact, the way to implement lossless source coding, okay? And in order to get some intuition, I propose you to make a game. So we'll play the hangman game. So nobody will die, huh? Don't be afraid. But I would like you to play, to propose letters, and more importantly, I would like you to explain me your strategy. Why do you propose these letters? Okay, so let's start. I go here. And I need light. So, please. E. Very good. But why? Most frequent letters, thank you. That's a very good idea. I need another ID, so I need you to, we need only 2 IDs. So please propose other letters. I, yes. And why?
I mean, my idea was that usually there's an I before an E.
Yeah. Okay, indeed, there are correlations in letters, and we already have the 2 IDs, so you won. Well, okay, then I can tell you that it is a first name. It is a female first name. It is the first name of the project manager of the MoleculArXiv project. So maybe you can already, Alice, very good. So we have 2, so thank you for your participation. And we already have the 2 IDs that will explain compression. Indeed, so there are 2 winning IDs. The first one is that there are some letters that are more frequent than others. So in math, you call this probability. So we will use the probability of the symbols of the occurrence of the letters in order to be able to reduce or to compact the data. And the second idea is that there is some correlation between successive letters, and this will be, so this is also called dependence in probability, and this is also the second idea that we will use in order to be able to compress data. Okay. So why is it the same? So let's make it more clear. There is indeed an analogy between this game and a compression problem. So in the game, we had a word that we would like to guess, and here it could be a data that we would like to compress, so for instance an image, and the answer to the question yes or no, you can see that as 1 bit of the representation of the data. Okay, and each time I answer you a question yes or no, I remove some uncertainty on the word, and similarly, when I give you 1 bit of the data, then I remove some uncertainty of the data. Okay, and there is in the game a kind of protocol. You ask the question, is it an E, is it an A, or, and then if I answered, oh, there is an E here, so maybe there could be an I as you proposed, or so there is a sequence of questions that I ask, and this is completely similar to the structure of the data, of the compressed data, okay? And at the end of the day, so you would like to propose a minimum number of letters, and similarly, we would like to propose a minimum number of bits to represent the data, okay? So how can we exploit these 2 IDs? So this is what we will see in this lecture, but before that, I have to make you a computer scientist with 2 questions. So how to be a computer scientist in 2 questions. So if I have a sequence, okay, of n bits, how many sequences can I make? 2 to the power n. So very good. The number of sequences. So you are half of a computer scientist. So let's make the second half. So if now I have a set with data, so this is an ensemble, okay? And the cardinality of the ensemble is, yes, it will be this. Okay, this is the cardinality of the ensemble. And if I would like to distinguish all the sequences within this set, how many bits do I need to represent all these elements? log 2. Okay. So I need log 2 bits, cardinality of the ensemble bits, in order to represent all this set, all this data. Okay? You are a computer scientist. Very good. Okay, let's continue. And so I would like to introduce you Claude Shannon. Claude Shannon wrote this paper in 1948, and this is one of the most influential scientific paper almost ever. It had so Shannon was working on a communication. He tried to understand what was the fundamental, what was the basis, the mathematical basis of the problem of communication. Okay, so he was working at that time for Bell Labs. So Bell Labs was the research lab of the AT&T company. And so he wrote this paper in the internal, it was an internal journal, the internal journal of the Bell Labs. And then Weaver, another scientist, already recognized that it was a very important paper, and he proposed to Claude Shannon to republish it in a book such that it could be accessible to a larger audience. And that's why it was republished 1 year later. And as you can notice, the title changed just a little bit. It's from a mathematical theory of communication, it became the mathematical theory of communication. So that's why you can find the two citations. But it was, well, there are many, many great ideas in these papers, and this is what we will see today. Okay, and in fact, it was the beginning of a new field. And this field is called information theory. So what are these great or brilliant ideas? So the first very good idea is the fact that he models the communication in that way. So today it seems to be very natural, but at that time it was completely new. And this is the way he models information. So imagine there is an information source, so, something that will deliver messages. Then the message will be processed by the transmitter and sent through to a channel. And then the receiver will receive the message, will process it, and then will send it back to the destination. Okay. So this model is already a very interesting idea. And so what is a message? So a message can be whatever you want to send. So it can be an image here. And what is a channel? So there are 3 types of channels. Either you have no channel at all, or you have a noiseless channel. So you can imagine that you have a kind of a pipe, and the diameter of the pipe tells you how much data can flow through the channel. Okay. So it makes a constraint, and that will be a constraint on the rate of information that can flow through the channel. The channel can be also noisy, so it means that on top of this rate constraint, there will be also noise. Okay. And in order to deal with these perturbations, we'll propose, or we will implement, or we have to create some kind of coding, it's kind of processing. And when you need to compress the data, it will be called source coding. So for the noiseless channel, in order that the data fits into the pipe, then you will use source coding. And if on top of that you have also noise, then you need not only source coding, but also channel coding. Okay. Good. Okay. Yes?
You said that there can be there can be transfer without a channel.
There can be
Data transfer without a channel.
Without a channel? No, there is always a channel. But there are 3 types of channels. Okay, or I see, or yeah, I said there is no channel, or in the sense that there is no constraint. Okay, I talk to you. You can imagine we are in the same room. There is no constraint. You hear all what I, yeah. Okay. Okay. So, and we will go now into the math, but we'll go slowly into this math and all these definitions. So, the very first and nice idea of Shannon is to think that there is a limit. There is some kind of optimal compression, and there is a limit, and the limit will be in the rate. And this is already a very nice idea. The second idea that is also very good is to model the message as the realization of some random variable. Okay. And the third idea is that, okay, so here we are in a context of lossless compression. I would like to retrieve perfectly the data at the output. And he proposed not to look exactly at the same problem, but at a slightly different problem, in the sense that now we'll allow some kind of error between input and output, and then we will let this probability of error goes to 0 when the amount of data that we want to send goes to infinity. So here you might say, I didn't sign for that, right? It's not so clear. I mean, I wanted to have completely and perfect compression, and then you tell me, okay, no, you will have to end the end of the universe to send an infinite length message in order to retrieve perfectly your data. So I ask you to be a bit patient, and I will explain you only in a couple of slides why it was a very good idea. Okay, so but let's keep in mind that we slightly modified here the problem. So what is the goal? What is what do we want to achieve? So here we have the data. So yeah, there is some things that I have to explain about the notation. In information theory, when you have a sequence of n elements, what the notation is that we write it x to the power n. So it makes sense in a way because these elements, I mean, they are elements of the cottage and product of the ensemble x. Okay. Well, it's just a notation, and I will use it a bit because we will always deal with large sequences. Okay. Okay, so this is what I write here. So here we have a sequence of random variables, and we want to we will encode them. Okay, and what we would like is to have a representation here that is. Sorry. It seems that yeah. It depends on the place I have in the room. Okay, okay. So. So what we would like to have is that the length of the length of the encoded sequence is as low as possible. So we will minimize this length, and then we compute the average over all possible messages that we would like to compute. So this is the meaning of this one. Okay, and then we will. So this computes the average length for a message of length n, and then we would like to compute this length, but per symbol. That's why we divide it by n. Okay, so that will give us what is the minimum, or the representation, the number of elements that we need in order to compress the data, but computed per sample. Okay, and then we would like to find the best possible encoder. Therefore, we minimize over the two function encoding and decoding function under the constraint that the probability of error, okay, is below a given threshold. And then we let this threshold goes to 0. Okay? So this is the definition of the problem that we would like to solve. We would like to find the best possible compression. Okay? Then I defined another quantity. So this is the entropy. So this is the entropy. We will go later, in the next slide, I will show you and give you some intuition of the meaning of this entropy. But for the time being, just look, it's a very nice formula. Okay, it just depends on the distribution, and it's very easy to compute. Here, it's very difficult to compute. I mean, you have a limit, and you have an optimization problem to solve. Okay, and okay, ta-da, wonderful. This is the theorem. So it is beautiful. Here it says that this optimal rate that is very difficult to compute, and this is really what I want to solve, it is equal to something that is very easy to compute. Okay. And this, in information theory, it is the holy grail. When you solve that, you are the king or the queen of the world. Okay? So it is beautiful. So you have to, it's nice, right? So it says that there exists indeed a limit when you want to compress the data, and I can compute it. So now let's have some intuition of what this entropy is. Okay, so we will compute the entropy for a binary random variable. We look at 3 different examples. So here what I plot is that here on the x-axis, this is the probability of having a 1, for instance. And here on the y-axis, we look at the entropy. Okay, so imagine that you start with binary random variable where you have only zeros. The probability to have a 1 is 0. Okay, there is no uncertainty. You always know that the message will be 0, 0, 0, 0. It's just as here you say in Cargèse, weather is always good. I don't deliver you any information. I mean, you know that the weather is always good, right? So here there is no uncertainty, and the entropy tells you, so if you compute this formula, it says that the entropy is 0. There is no uncertainty, there is no information. Okay, you can look at another example when the probability is 0.2, which means that you have 20%, more or less 20% of ones that will occur. In that case, the entropy is much higher. It's 0.72. So, okay. And if the probability is 1/2, okay, you have almost as many zeros as 1, then the entropy is maximum. It's maximal, and its value is 1. Okay. So in a way, you can see that the entropy, it is a measure of uncertainty that you have in your data. It is also the measure of information that you want to delay or that you want to deliver in your data. Okay. And thanks to the theorem, we know that it gives you the number of bits per source symbol that you need in order to optimally compress your data. Okay. Okay, and now we'll go to the proof. Okay, so either you fall asleep, or you follow, but I do believe that the proof is not that complex and that you might understand the subtleties of the proof. So how does it go? We will construct a code that can indeed achieve this level of compression. So here I represent all the possible sequences, okay? So in this set, the big set, all the possible sequences that can occur, okay? So, and that's the data that I would like to compress. If you look at this ensemble, you can make a partition into non-typical and typical sets. So what is a typical set? It is a set that represents well the distribution. Imagine that you have a Bernoulli random variable with a probability 0.2. It means that it is all the sequences that are almost close to sequences where you have 20% of 1. Okay. What is interesting is that if you look at the non-typical sequences, the probability of being non-typical is very low. you can, as n goes to infinity, you can make the probability of being non-typical very low and below a threshold. And you can make, it will converge even to 0 as n goes to infinity. Okay, and then there are the typical sequences, and if you count the typical sequences, the cardinality of this ensemble will be 2 to the power n times the entropy. Okay, so once I did this computation, I can propose you a code scheme, and the code scheme will be the following. All the non-typical sequences, they will be mapped onto the same index, the same representation, and all the typical sequences, they will have a different representation, okay? Which means that, so we can already compute the rate of such a scheme. So how many bits do I need in order to represent all the typical +1 indices? Well, when n is when n is large, well, the +1 is not very, I can neglect the +1, okay? So how many bits do I need in order to represent all the typical sequences? So that's what, that was our second, second rule to become a computer scientist. So, yes?
N times h of x.
Very good.
2 of a.
Yes, exactly. So the rate, so when I encode n symbols, I need n times the entropy of x bits in order to represent these n symbols. So what is the rate? So the rate, I will compute it in bits per symbol, so I will divide it by n, and I need, therefore, hx, so the entropy of x bits in order to represent each symbol. Okay. Now I can compute the probability of making an error. I make an error if I am non-typical, and the probability of being non-typical, I saw previously that the probability of error is bounded by epsilon, and I can make it tends to 0. So you see that just by counting the sequences, I'm able to construct a code that rate is the entropy of x. Therefore, the minimum, so the optimal one will be better, and so the optimal will be upper bounded by entropy of x. Okay. And what is beautiful in this proof, so I didn't go into the details on how to count, but what I would like to share with you is that the only thing that we need in order to show this theorem is a law of large number. So we know, you know, when you did a course on probability, it is one of the first theorems that you've seen. So, I mean, with very little background in math, you are able to show this kind of theorem. So it shows also how beautiful this result is. Okay. Now, I'll go back to our original problem. So the original problem is to be able to compress the data, but losslessly, without any error. Okay? So now I define the optimal compression rate for lossless source coding, but the probability of error is 0. So I define the same, the rate, the optimal rate. So again, I compute the average length of the encoded sequence of the compressed data. I will minimize this, this length over all possible input and output, encoder and decoder, under the constraint that the probability is 0. And then, in the same paper, there is also the proof that the rate for this scheme is also the entropy of x, in bits per source symbol. So how does it go? So here, Shannon proposed a construction of a code. So you have, imagine that you have all the symbols that you would like to encode with some probabilities. And for each symbol, the first thing that you have to do is to determine the length of the code words that you will need in order to represent a symbol. And so you see that it is related to the probability of occurrence of such a bit. So it is minus logarithm of the probability, and then you take the integer, the first integer bigger than this one, than this value. And then you assign a code word of this length for each symbol. And this can be done with such a binary tree. You start from the most probable is not that important, but you apply a prefix-free constraint. What does it mean? Is that once you have determined the length of a code word, you erase all the descendants in the tree, such that you cannot use such a code word for other symbols. Okay. So, for instance, first we had the length. Imagine that you have the length 2. So, for instance, we decide that it is 0, 0, and there will be no other code words used. You cannot use 0, 0, 1 or 0, 0, 0. And for the other symbols, then you compute its length and it was 3, and then you get all this representative. So doing so, you know how to decode, right? Since no code word is a prefix on another code word, when you recognize a 0, 0, you say, oh, okay, yes, it is a code word. I know that it was related to this symbol, and then you can decode that way. Okay, so this is a way to encode and to decode with a probability of errors that will be 0. Okay, and now you can compute what is, there are two things that are here interesting and very important. The first thing is that here you have a variable length code, which means that all the symbols will not have the same length. So this is a way to exploit the fact that there are some symbols that are more frequent than others. You can think that in the Morse, for instance, this rule was already used. E is very frequent, and in the Morse code, E is represented with a dot, okay? Something that is very, very small. So it's very intuitive. I mean, the symbols that are very frequent have a very short code word, okay? But the representation is variable. I take a little bit of time here. It's because for us, in our problem, the fact that data are coded with variable length code, it might be a problem for the synchronization. And with all the talks that we had with the deletion and the insertion, you already know that there might be problems here if we lose synchronization, okay? So variable length is a very important characteristic of the way to achieve or to do compression. And then the other one that is important is that this prefix-free constraint, and this makes the code being having a 0 error. Okay, we can decode the data. Now, what is the rate? Okay, and so the rate, it's computed here in this theorem. So here I rewrite what is written above. So what you can show is that if you encode with such a strategy n symbol, the average length of this code will be between the entropy and the entropy plus 1 over n. Okay, so this is one code. So we know that the best code, okay, will have a rate that will be smaller than this one. And it will be, so if you let n goes to infinity, the two bounds are equal, okay, and therefore, okay, so no, I'll say it again, okay. So this code in particular, if you let n goes to infinity, okay, so since the upper bound and the lower bound and the upper bound will be equal, so this code will achieve a rate of the entropy, and since you know that the optimal rate will be better by definition, so the rate of such a code will be smaller than the entropy of x. Okay? So here we constructed a code that can achieve indeed the entropy of x. So, and we did it twice. We did it once for the vanishing error problem, and we did it once also for the 0 error problem. Okay? And we have shown for both cases that this code construction would have a rate that is smaller than the entropy. But we know that the 0 error problem is more difficult than the vanishing error problem. Therefore, I can have also this inequality, that the optimal rate for the vanishing error problem will be lower than the rate for the zero error problem. Okay. But can we do better? We just constructed one code, right? And the answer is no, we cannot. We cannot. There is a converse that tells you, indeed, we cannot do better than this rate. Okay, and therefore, the optimal rate for both problems is the entropy of X. And that's why, so thank you for being patient, but that's now that we can understand why it was a very good idea to go to the vanishing error problem. Because, in fact, Claude Shannon did not have the proof of the converse for the zero error problem. He had only the proof for the vanishing error problem. So you can see that the vanishing error, it is a proof technique. It was used in order to be able to compute this optimal rate. And the true interest of Shannon was the zero error problem. He's a builder. I mean, he's proposing new things. He's proposing new algorithms, and they have to work. So his true interest is really in doing codes that can compress and such that you can retrieve perfectly your data. Okay. Okay, so I have a next slide. That is, one more thing. So in fact, the proof came later, and it was done by Macmillan, but in '56. The converse for the zero error problem was done later. And I have a next slide that is maybe more for experts. It's just to remember, but you can follow anyway. How does this converse work? So the converse, in fact, today we don't look at the converse given by Shannon. We mostly cite the one by Fano. It's due to the Fano inequality, where you have a link between entropy and the probability of error. So it was done proposed in '52, and so it's also very funny because in fact there is no, it is not written anywhere, this Fano's inequality. It was only in course notes. Fano was teaching information theory at MIT, and there is only course notes where you can find this Fano's inequality, this proof, but that's quite funny because it's maybe one of the most used inequality in information theory, and there is no paper for that. Okay, and the second one, due to Macmillan, it's based on something that is called Craft inequality. You count sequences in a binary tree. So there is some similarities with the code construction of Shannon, but that's all what I wanted to say about the converse. But okay, maybe just one word. Converse is really the difficult task in information theory. Constructing is usually okay, but showing converse is really the difficult task. I mean, I see some information theorists and they say, oh yes, it's true, the converse is difficult. Okay, so now we can ask the question. So the vanishing error, it's a very nice trick in order to show theorem, okay? And so you can say maybe it's a universal trick. You can use it for many problems. So let's look at what it is. So vanishing error, so I rewrite here the definition that we had. So what is the optimal rate? So this is the first line. The second line is the optimal rate that we have when we have the zero error constraint. And in fact, if you look closely, you can rewrite the optimal rate of the zero error problem, where we see that it is very similar to the vanishing error rate, but you have just exchanged the two limits. So why is that? Look at this definition here, okay? So you fix n, okay? So limit, you fix n, and then you let the epsilon goes to 0, okay? So when you have a sequence of size n, okay? And then, and then you will ask that the probability of error is bounded by this epsilon. But because the length has a finite length of n, the number of probabilities that you can have, the number of values, it is discrete. So if you let epsilon goes to 0, in fact, since it is discrete and epsilon goes to 0, it can only be 0. Okay? So the zero error problem is just because we exchange the two limits. And now you remember on your math courses, and the teacher always told you, oh no, be careful, don't exchange the limits, or be careful, you have really to prove that they are equal. And it is most of the time a very difficult task to show that when you exchange the limits, the two are equal. So we can now answer the question, are in general the rates always equal? So we've seen that it is true for our problem, so the problem of lossless source coding. We can exchange the two limits, but there are many problems where we cannot. And this is an example where indeed you cannot, so this is lossless distributed source coding, so imagine you have two cameras, for instance, looking at the same scene. You would like to compress the two images, but there is no cooperation, no communication between the two cameras. And, but it's only at the decoders that you can merge the two data. And then for this problem, you can show that the two, you cannot exchange the limits. Okay, okay. Good. But what is the winner? There is a winner, because in fact, Shannon code, it's not an optimal code, okay? And there is a winner, and the winner is due to Huffman. It's, yes, it is due to Huffman, and it works so the following way. So there is a recursive rule in order to construct the data compression. So you have to merge the two least probable symbols, and then you differentiate by 0 and 1, and then you repeat. So yeah, here I take an example, and I show that, in fact, Huffman is better than other codes that has been proposed in the literature before him. It was the code of Shannon that I presented, for instance. The proof of optimality is the following. He proposed some rules that an optimal code has to satisfy, and then you show that these rules are indeed necessary and sufficient. And these rules are satisfied by the code that he proposed, and then that these rules are indeed necessary and sufficient to achieve the optimal rate. Okay, okay, so we have a winner. There is also a nice story about the Huffman code. In fact, Huffman was a master student in the course of Robert Fano. Robert Fano was teaching information theory in '52 at MIT. And he said, okay, so you have two possibilities. Either you take the exam or you make a project, okay? And yeah, Huffman said, okay, I will go for the project. And the project was, indeed, to solve this problem, to find the optimal code. But Fano never said that he didn't have the solution, that he didn't have the solution, that Shannon did not have the solution either, and he found it. So that's a very nice story, right? And in fact, you see that in '52, only 4 years after the first publication, the problem was solved, okay? So that's all about lossless source coding. So let's make a summary. So with a take-home message. So if you want to be able to survive in this course, but also, I mean, in data compression, so this is the things that you have to remember. In data compression, in lossless compression, there is indeed an optimal rate, okay? And this can be easily computed by the entropy, and it gives you the number of bits per source symbol you need in order to represent your data. What is also very important is that the optimal code is variable length, okay? The code words, so the presentation of the symbols don't have the same length. And there is an optimal code, and it is the one of Huffman. There are others, and the differences are mostly in the implementation. Well, that's level 1 summary. If you want to be a little bit more expert in data compression, you've seen that there is this notion of vanishing error and zero error. Vanishing error, it's a trick in order to get some proof and show optimality. We've seen that in some cases, the two problems are equivalent. So in particular, when you have one source, one destination, one transmitter and one receiver. But if you have more, in more complex situations, this might not be the case. Okay? When you have two separated sources that are not allowed to communicate and one destination, then it's no more the case. And okay, there is something else that I would like to say about lossless source coding. It's something that I've not presented in this course, but that might be of interest for us when we look at DNA-based data storage. If you look at the, and it is written here, surprisingly, even if you have independent symbols, it is better to encode jointly. It's not at all intuitive. And it comes from this formula. So if you look at the optimal lengths of a code word, okay, the optimal bounds that you can find for this optimal length is between the entropy and the entropy plus 1. But these two bounds are true bounds. It means that there are some distribution for which you can achieve the entropy, but there are other distributions for which you cannot achieve entropy. You can only have entropy plus 1. But the distribution is something that you cannot control. I mean, this is the data that I give you. I give you an image. It has the symbols that it has a given distribution. You cannot control this distribution. So maybe you have bad luck, and you are in a case where the distribution, you will have to pay one more bit per each symbol, which can be a lot, okay? So that's why the only way to decrease the upper bound, it's the only way to do it is to increase the size of the data that you jointly encode, okay? Okay. Well, so we've seen entropy coding, and I would like now to go to the next step, and we will look at lossy source coding. And maybe I can take a few questions before we go to the next. Yes?
I have one, because the entropy only takes into account the probability of the symbols. So where are the correlations?
Yes.
So the correlations should allow you to
Yeah. Yeah, so all this part was about how to compress independent symbols, and the correlation, I will tackle this in the prediction and transform. Yeah, yeah. But we can do all the same theory, but then indeed you have to take the vector. Yeah. Well, it was mostly in order to go step by step that I went to this. Okay, very good. So now, lossy source coding. So why do we do lossy source coding? It's because if we don't do that, I mean, it's not, our data center will already cover the Earth. I mean, we need to do lossy compression for image and video because it takes a lot of data. So maybe we can just make a small computation here, just to get imagine that you have a HD, high definition, so that's what you all have on your smartphone, okay, have HD. So it means that I have the number of pixels of your camera. So you have almost 2 million of pixels. So I imagine that you make also color, right? You don't have black and white. Yeah, okay, you have color. So which means that So here I'm counting the number of bits I need in order to represent HD video. Okay. So this is the number of pixels. So my pixels, they are coded on. So I have 3 channels for the colors, and but first, okay. So there is a small subtlety, but here, so each pixel will be represented by 8 bits. Okay, and then we have. So your eye is much more sensitive to black and white. Black and white rather than color. Therefore, we use a format. Well, it's very technical, but it's called 420, where so the color is represented by here what we call the luminance. So this is more or less black and white. And then you have 2 other channels, U and V, for the chrominance. But since your eye is less sensitive to colors than to the black and white, to the luminance, so we subsample this data. So you have 8 bits per pixel for this, and you have 8 bits also per pixel here, but the size is, of the images is divided by 4. So here I will have 1 plus 1/4 and 1. Okay, so that's in order to represent all the pixels. Okay, and well, that's just for one image. But you look at the video, right? And so imagine that you have the rate, classical rate is 25 hertz, which means 25 images per pixel. 25 frames, 24 images per second. So here it makes 12. Here you have 25. So this is 4 times 3. So here you have 100 and 6. So it will be 600 megabits per second. Yes, okay. So your video, the video that you take on your smartphone, it means 600 megabits per second. It's huge, right? So there is a need to do compression in a way where we admit some losses and to admit some losses in order to reduce the rate. I mean, I don't have this rate, right? If you want to send such a video, it will not pass. So basically, today, this kind of video, we can compress it with 1 megabit per pixel, per second, okay? So well, this is the size of this is the size of each. Yes, this is a.
It's full HD, not
yeah. So yeah, the images that you take, it's. Yeah. Okay. Okay, so we need to do lossy compression. And how do you do? We do that. So it's really. Okay, so we go a bit through theory again. Let's go back to theory. And there is a guy named Claude Shannon who wrote a paper in 1948, and the paper was in different parts. In one of the parts, he already mentioned what can we do when we have continuous sources. So, okay, and he already mentioned that the only way to do that is that because when you have a reel, right? Imagine that you have a reel. So that maybe that's a bonus question to be a computer scientist. If you have a reel, how many bits do you need in order to represent a reel? 1, 2, sorry? Sorry, I did not hear.
Infinity?
Yes, you need infinity. So it's not possible to represent. So you need an infinite number of bits in order to represent a reel. So here, what he said is that if you want to represent a reel, so a continuous source, then there is no, you need to have some distortion. You have to make errors. And then there will be a trade-off between the number of bits you need in order to represent this data, these reels, and the distortions that you will have, okay? And he introduced something that is called the rate distortion theory. Okay, so let's take the operational point of view of this rate distortion theory. So here, you have your data, you want to encode it and decode it, but you will allow some kind of distortion, some kind of errors between input and output. If I take a very specific encoder, so I fix the length, I fix the encoder and I fix the decoder, then look in this plane. So this is, here I represent the rate that you can achieve versus a distortion. So for one particular encoder, I will achieve 1 point, okay? So one rate and one particular distortion. If now I look at all possible encoders, all possible decoders, and all possible lengths, then I will get full samples, full dots, I mean, for each possible construction that I get. And what I'm interested in here is the best trade-off that we can achieve, okay? So, and the best trade-off defines, so here we have the region of achievable rate distortion, and the definition of this operational rate distortion function is the following. So it's very similar to what we had before. So we would like to minimize the rate over all possible encoding and decoding function under the constraint that the distortion is below a threshold d, okay? And then I will look at this when the infinity, when the length of the sequence goes to infinity. So you can imagine that, so previously it was very difficult. This is even more difficult to solve, right? So how can you do that? You can take all the people from all the Earth, you say, oh, you have to work hard, and maybe each of you will get a point here, and then we can maybe have some kind of estimation of this curve. No, okay. No, because what? There was a guy called Claude Shannon who gave us the answer. And the answer is here. So he defines this function again. It's something that is quite easy to compute. It depends on only one symbol. There is no more the limit. This is something that depends only on the distribution, on the joint distribution between input and output, on the marginal, etc. And he shows that, 48, right? It's again, it's beautiful, right? It does good. When you see this kind of nice results, it does good. So how does it look like? Well, still, the problem is not completely solved because now, so you remember with the entropy, you just had to compute an average over the probabilities. Here there is one problem that needs to be solved. There is a minimization to compute. But it's only one variable. Okay, so let's look at some kind of some example of this rate distortion function. So when it is discrete, you will have so it's first rate versus distortion. So there is something that is quite intuitive, that when the rate increases, so you add more bits, the distortion will decrease. This is clear, okay? So when the data is discrete, also, if there is no distortion, we know that we can retrieve exactly the data, and what is the rate, so we can have a zero distortion, and the rate that we will achieve in that case is the entropy. So this is what we've seen before. And in some cases, we can even have a closed form of this curve. This is a case when you have a binary variable and the distance is a Hamming distance. So the distortion that you compute is made with this. This is a L1 norm, right? And here you have a very nice formula. So when it is continuous, you have the same kind of shape, okay? But there is one difference. So as we've seen, so what is the number of bits that we need in order to represent a real where when the distortion is zero, it's infinity. So here the curve will go to infinity in that way, in that direction. And now if you want to, if you don't send any bits, you will have a distortion, but this distortion will not go to infinity. It will be bounded. It will be bounded, and if the distance that you consider as a squared error is a L2 norm, then you can even you can even compute this distortion. Okay, so maybe we can have a small example here. Imagine that you have a Gaussian. You have a Gaussian here. So this is a Gaussian distribution. You have a mean here. Okay, and you have a Euclidean variance. And my question is, you don't send any bits. Okay? You don't send anything. And what is the best guess that you can make on the realization of this random variable? You know the distribution, but you don't send anything to represent. So what can you do? What can be the x hat? What can be the representation of one particular symbol? The mean value, very good. Yeah, so 0 if it's a... And so indeed, in that case, you don't send anything. You always represent your data by the mean. And in that case, if you compute the distortion, x... So this is mu. And this is exactly the definition of the variance. Okay? So this is exactly the variance. So it means that even if you don't send anything, the distortion will be bounded by the variance. Okay? Good. And for the, if you have a Gaussian and a square, so the L2 norm as a distance, and you can even have a closed form expression of this curve. Well, in fact, that's the only case where we have a closed form solution. Huh? Well, but it's not a problem because there are ways in order to, there are algorithms in order to compute the curve. Or, now you may know, there was a guy, the guy was called Claude Shannon, and he found a bound. And the bound is called the Shannon lower bound. So and this bound allows you to have an analytic, a closed form expression for the curve. Okay? And so in order to get the bound, you just say that you assume that the error that you make is independent of the source symbols. Well, it's a little bit harsh, but well, at least it is exact when it is when the data is Gaussian. But what is more important, so here I take another distribution, I take the Laplacian, and what you can observe is that, so the true distortion rate function is in blue here, and the Shannon lower bound is in black, and in fact this bound is very tight. If you have 1 bit per symbol, the two curves are already equal, almost equal. So in fact, so it is again, at least we have a way to have a closed form expression of this bound for high rates, but high being only a rate that is greater than 1. And this was shown later. So you see, it's only in 94 that we had this kind of result that shows that indeed the Shannon lower bound is tight. Okay, so just have a look at some examples to make it a bit more, more practical or more that we see a few things. So the Shannon lower bound has always the same expression. So it will always be a constant times the variance of the random variables times 2 to the power minus 2r. It's always the same. And the epsilon, so this constant, depends on the distribution. So if you have a uniform distribution, okay, then the constant will be 0.7, 0.8 for Laplacian, and the Gaussian, it will be 1. So that's something that is quite interesting here, is that the Gaussian has a greater constant, and in fact, you can show that among all possible distribution, the Gaussian has the higher constant, so meaning that for a given rate, you have the higher distortion. In other words, the Gaussian is a more difficult random variable to compress. Okay. I think it's a good time to stop because after that, I will go to explaining why this and this is a good way to implement lossy source coding. And then finally, we will go to take into account memory. And finally, we will be able to look at what happens for DNA-based data storage. I will be more quick on the last part. It was important for me to introduce the basic notion such that we can build. And yeah, so I'm happy to answer a question if you have. Yes?
So if I understood correctly, it's now independent distributions for each position of the message. Is the same math equally usable for dependent probabilities, or is it then not usable? Just having the expectation value of a dependent distribution would also work for this.
Okay.
Yeah.
It's a natural question. I mean, in fact, if you have dependent, one way to do is that instead of looking at what sample, you can replace it by a vector, and then you can do all what I said before, but you work with vectors. That's one way of doing it. The problem if you do that is that the complexity will grow exponentially with the length of the vector that you consider. That's why, and I'm already spoiling a little bit what's coming next. That's why we go to a prediction and transform in order to be able to have a complexity that will remain hopefully linear with the length of the vector. Yeah. But all the theory you can rewrite. You just say that instead of an x that is of dimension 1, it is of dimension whatever. Yeah. Okay. Do we have other questions? Okay, so I suggest we go for a break.